If you remember, in the last lecture we have talked about vector subspaces. So, today we are again going to talk about a very important concept from the vector spaces, that is basis and dimension of vector subspaces. So, in most of the machine learning algorithm we need to represent our input data, that is in terms of feature vectors, as a linear combination of certain vectors, that all the feature vectors we want to write as linear combination of a set of vectors. Those set of vectors may be linearly independent or they may be orthogonal. So, to write all the feature vectors of our data set in terms of linear combination of these vectors, we have to find out that particular set of vectors. So, these vectors form a basis for the feature space. Today we will learn about the basis of the vector spaces. The concept of basis is really important, especially in the case of dimension reduction or the recent algorithm like dictionary learning based algorithm. Further, in wavelet based algorithms we approximate any function as the linear combination of set of orthonormal functions those we have generated from the mother wavelet. So, let us come to the definition of basis. So, mathematically speaking, the definition of basis is given as let Vf be a vector space. So, we are having a vector space V over the field F. A basis for V is a set of linearly independent vectors in V which spans the vector space V. Now, so what should be the qualification to be a basis? The first, all the vectors of that set should be linearly independent. Number 2, you take any vector from the vector space V, that vector can be written as the linear combination of the vectors of the basis set. There are two types of vector spaces, finite dimensional vector spaces and infinite dimensional vector spaces. So, if the basis of a vector space V contains the finite number of vectors, then we say that it is a finite dimensional vector space. Otherwise, we say that the vector space is an infinite dimensional vector space. A vector in basis is called the basis vector. So, if we talk this definition mathematically, so what we are having, a set B having vectors, let us say V1, V2 up to Vn is a basis of a n dimensional vector space V if the set of vectors V1, V2, Vn is linearly independent that is the first thing we need, and the second thing is for any vector V belongs to the vector space V, we have V equals to alpha 1 V 1 plus alpha 2 V 2 plus alpha n V n, where alpha 1, alpha 2, alpha n are scalars from the field F. So, this is mathematically we can define basis in this way also. So, if you see some example of the basis, so if you take V equals to R2 over the field R, then if you take vectors like 1 0 and 0 1 in R2, then this set forms a basis for V. The first thing, both of these vectors are linearly independent, and the second thing, you take any vector V from R2, we can write that vector, let us say you are taking some vector alpha beta, arbitrary vector belongs to R2, then we can write alpha beta as alpha times 1 0 plus beta times 0 1. So, what I want to say that this set spans whole R2 space. Similarly, if you take V equals to R3 over the field of real numbers, then one of the possible basis is 1 0 0, 0 1 0 and 0 0 1. If you take V equals to R and R, then one of the possible basis is 1 0 0 0, 0 1 0, 0 0 1. So, all these are n tuples vector having one of the element as 1 and rest of the elements are 0. So, all these three are called standard basis for R2, R3 and Rn respectively. If we take a vector space like this, so R2 by 2 matrices having real entries. So, certainly this V over the field of real number forms a vector space. We have seen it in previous lectures. Now, what will be the basis of this? So, basis of this will be so this is one of the possible basis for this vector space V. Here you can notice all the vectors, those are 2 by 2 matrices are linearly independent, and any 2 by 2 matrix can be written as the linear combination of these 4 matrices. If I change this vector space, let us say V equals to M2 by 2 set of all 2 by 2 real symmetric matrix. Then what will be the basis? Certainly this set over the field of real numbers will form a vector space, and what will be the basis? One of the possible basis will be given as 1 0 0 1, sorry 1 0 0 0, 0 1 1 0 and 0 0 0 1, because this is space of symmetric matrices. So, these two elements will be equal to have symmetric to be the matrix symmetric. So, this basis will be having 3 vectors, while this is having 4 vectors. So, these are some of the examples of basis of different vector spaces. My next definition is dimension. So, what is the dimension of a vector space? The dimension of a vector space is nothing, just the number of elements in the basis or number of vectors in the basis. So, formally I can say the number of vectors in a basis of Vf is called the dimension of the vector space Vf. So, as you have seen example, the dimension of vector space R2 over the field of real number is 2. The dimension of vector space Rn over the field of real number is n. The dimension of the vector space of all 2 by 2 real matrices over the field of real number is 4. If you are taking the vector space of all m by n real matrices over the field of real number, then dimension will become m times n. If you take the vector space of all the polynomials having degree n or less, then the dimension of that vector space will be n plus 1, because we will be having n plus 1 elements in the basis. Similarly, dimension of vector space of all polynomials is infinite. Why? Because it is a infinite dimensional vector space. We can write any polynomial from this vector space as a linear combination of finite number of vectors from that basis. However, basis will be containing the infinite number of elements. Now, come to some important results related to the basis and dimension. So, my first result is let V1, V2, Vn be a basis of a n dimensional vector space Vf. If S be a subset of vectors having more than n vectors, then the set S is linearly dependent. So, what I want to convey that if the dimension of vector space is n, any set containing more than n vectors will be linearly dependent, because in a set you can have at most n linearly independent vectors. And if you are having such a set where you are having n linearly independent vector, then that set will be a basis of that particular vector space. So, what in other words I can say that the basis is a maximal linearly independent set of a vector space. If you are having any other vector in that set, that vector can be written as a linear combination of rest of the vectors. My second result is let V1, V2, Vk be a linearly independent subset of a n dimensional vector space V over the field F, where k is less than n. Then S can be extended to a basis of Vf. For example, suppose I am having a vector space R5 and I am having 3 linearly independent vectors of R5. So, what I can do? I can include 2 more Li vectors to that set of 3 vectors, and then I will be having 5 linearly independent vectors in R5, and then this set will be a basis of R5. Another important result is like let Vf be a finite dimensional vector space, then any 2 bases of V have the same number of vectors. We can have multiple bases for a vector space. However, each of the bases will be having the same number of vectors. that is equals to the dimension of the vector space. So, for example, if we talk about R3R, you have seen that one of the set of vector 1 0 0, 0 1 0 and 0 0 1. This particular set forms a basis for R3 over the field of real numbers. If I take another set of 3 vectors in R3, let us say 1 0 0, 1 1 0 and 1 1 1. So, again these are 3 vectors in R3 and this is a linearly independent set. So, B2 also a basis for R3. So, we can have many other bases where we are having 3 Li vectors from the set R3 from the vector space R3 as a basis, but the common thing is all these sets will be having 3 vectors. My next result is let V be a vector space over the field F and it is finite dimensional. If you take 2 subspaces of V, let us say S1 and S2, then dimension of S1 plus dimension of S2 equals to dimension of S1 plus S2 plus dimension of S1 intersection S2. So, we have written S1 here, it will be S2. So, dimension of S1 intersection S2. We will see this result by this example. Suppose we need to find out the basis and dimension of the subspace S of R3 given as S equals to x1, x2, x3 such that x1 plus x2 minus x3 equals to 0. And we are having another subspace of R3 that is W given by vectors x1, x2, x3 belongs to R3 such that x1 equals to x2 equals to x3. So, how to find basis of these? So, my vector space is R3 over the field of real numbers and I am defining my set S as the space of all the vectors x1, x2, x3 belongs to R3 such that x1 plus x2 minus x3 equals to 0. So, in the previous lecture we have learned that how to prove that S is a subspace of R3. Now, we need to find out basis of S. So, here I can write x1, x2, x3 belongs to R3 such that x1 plus x2 equals to x3. So, I can write it x1, x2 and since x3 equals to x1 plus x2. So, I can replace x3 as x1 plus x2. This I can write as x1 1 0. So, 1 is coming from the first component. In second component we do not have any x1. So, x1 is 0 and then 1 plus x2 0 1 1. So, here I can write the basis of S is containing 2 vectors 1 0 1 and 0 1 1. Hence, dimension of S equals to 2. So, in that way we can find out the dimension basis and dimension of a vector space. Take another example, there again V equals to R3 over the field of real number, and we are having W as x1, x2, x3 such that x1 equals to x2 equals to x3. So, what kind of vector we are having in W? Where all the 3 components are equal. So, for example, 1 1 1, 2 2 2, minus 1 minus 1 minus 1, all these kind of vectors. So, certainly the basis of, I can write it x1, 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 because x2 equals to x1 and x3 is also equal to x1, belongs to R3. So, what is this? It is x1 1 1 1. So, the basis of W is having only one vector 1 1 1. So, any vector of W can be written as some scalar times this 1 1 1. So, dimension of W is 1. If you need to find out basis of S intersection W, then what is S intersection W? It is all vectors x1, x2, x3 belongs to R3 such that x1 plus x2 minus x3 equals to 0. This condition is coming from the subspace S, and the condition from subspace W is x1 equals to x2 equals to x3. So, this I can write x1, x2, x1 plus x2 such that this I have written by this condition such that x1 equals to x2 equals to x3. So, if I take x1 equals to x2, then I can write it x1, now x2 equals to x1. So, x1 and then x1 plus x1 is 2x1. However, what I need? I need all the 3 components should be equal. So, in this case what we can have, the only possibility is that it should have the 0 vector, because we need x1, x2 and x1 plus x2 all 3 are equal. It will be only when x1 is 0, x2 is 0, and so that x1 plus x2 also become 0. So, this is the basis of S intersection W, hence dimension of S intersection W is 0. Why 0? Because I told you earlier that the vector space containing the 0 vector can be spanned by the empty set, by the basis phi, empty basis. So, there is no element in the basis, hence basis is dimension of S intersection W is 0. So, this is the way for finding the basis and then dimension of a vector space. Let us take one more example. Find the basis and dimension of S1, S2, S1 intersection S2, where S1, S2 are the subspaces of R4 over the field of real numbers. As I told you, the intersection of 2 subspaces also a subspace. So, again S1 intersection S2 is also a subspace of R 4. So, let us find out the basis of S 1. So, S 1 is given as x 1, x 2, x 3, x 4 belongs to R 4 such that the first constant is x 1 plus x 2 minus x 3 plus x 4 equals to 0. The second condition is x 1 plus x 2 plus x 3 plus x 4 equals to 0. So, what we are having here, by adding these two conditions, what I can write, x 4 equals to minus x 1 minus x 2. Now, from the first condition I can write x 3 equals to x 1 plus x 2 plus x 4. If I substitute the value of x 4 from here, that is minus x 1 minus x 2, I can get x 3 equals to 0. So, let me write it here now using these results. So, x 1, x 2, x 3 is 0 and x 4 is minus x 1 minus x 2. So, it is, if I take x 1, it is 1, 0, 0 minus 1 plus x 2 0, 1, 0 minus 1. So, here basis of S 1 is 1 0 0 minus 1 and then 0 1 0 minus 1. Hence, the dimension of S 1 is 2. Similarly, you can find the dimension of S 2 using the same procedure, and you will find that dimension of S 2 is coming 1 0 2 1 and 0 1 1 2. So, hence basis of S 2 is given by these two vectors and dimension of S 2 is 2. So, now dimension of S 1 is 2, dimension of S 2 is 2. So, dimension of S 1 plus dimension of S 2 is 4, which is equals to the vector space, dimension of the vector space R 4. Hence, dimension of S 1 intersection S 2 is 0. So, the basis of S 1 intersection S 2 contains only 0 element, which says that if you put all these 4 conditions together, the solution will be x 1 equals to x 2 equals to x 3 equals to x 4 equals to 0. All 4 components are 0. So, in this lecture we have learned the concept of basis and dimension. In the next lecture we will learn another very important concept of mathematics related to the machine learning, that is linear transformations. These are the references for this lecture. Hope you have enjoyed the lecture. Thank you very much.